So let's see, today I'll discuss sum of normal random variables and also the center limit theorem. Last time, in fact, the previous lecture was a little off. It wasn't joint PD, but it was on sum of, say, geometric random variable, and you realize that when you sum them, you will get a negative binomial. And then when you add the negative binomial random variables, you get another negative binomial. So this is something similar to that. Now, so we have x1, x2, up to xn, say they are normal. They are all normal, say, let's say we have mu and sigma squared. So those are the things that we have here. And we want to see what this is. X equals, say, x1 plus x2 plus xn. Well, in fact, I will post some notes on how to, in fact, prove this thing. We can prove it using certain things that we cannot prove. So, but anyway, if assuming that those theorems, we know those theorems, then we can prove that this is in fact normal. So we can show that this is normal. Show that x equals x1 up to xn is normal. And we are assuming that these are I, D also, so I'm not sure if I discussed I. I guess I did last time. The first I is independent. ID means identically distributed. So that's in fact, this means they're identically distributed. They have the same distribution, normal, mu and sigma squared. And independent means they're independent. So if we put them together as a multivariate and random variable, then the joint PDF splits as the product of each PDF, each marginal PDF. But that's something else. That is, don't confuse this thing with the other one. So what we had before was, if I say, let's put something else. So if this is, we consider them as one variable, one random variable, multivariable, multivariate, then the PDF of this thing, fx1, x2, xn, splits as marginal. So if it will be fx1, x1, fx2, x2 times fxn, xn, right? So, and since all of them have the same distribution, then this will be f x1, f x2 up to f xn. This is what we in fact discussed before, and the idea in fact gives us the independence in fact gives us this, and the ID gives us this. Independence gives us this split, and this second one gives me this thing, that they are in fact the same function of different variables, but the same function. But this is something else. This is different from this. So what we have here is when we add them. Okay, so what happens when we add them? We can, as I said, we can show that when we add them, if we have this situation, then that's also normal. But what is the expected value and variance of this x? So let's find e of x and the variance of x. In fact, when we say this is normal, we need both of them, right? This is the mean and this is the variance, so or expected value and variance. So let's find that. So e of x, in fact, is e of these xn, and we know that the expected value commutes with addition, and they don't have to be independent in this situation. They can be just not independent. This happens for both. So that is e of x1, e of x2, up to e of xn. And we know each one of them is mu, so we get n mu. Variance is a variance of x1, x2 up to xn. Now for variance to split like that, we need ID. This one doesn't need, independence. This one needs independence. So this also splits as, what's the variance of x1 up to variance of xn. And that is n sigma squared. Okay, so we can say that this x is in fact normal with, so this is normal with, and it is normal, in fact, not just normal, n mu and n sigma squared. Okay, so let me erase this. So that's what we found. Now, what is the? I guess we maybe I discussed this before, but let's also look at this. What is the say distribution of mean of this thing? So what is distribution of 1 over n sigma xi I from 1 to n? So this is in fact what we call x bar, and let's put an index here n, so it means that the mean of or average of n random variables. So we discussed this before, but this is also, we say it is also normal, because what we are doing is nothing. In fact, we are multiplying each one of them by a constant. So just a remark here, if x is normal, ax is also normal. Okay, so that's much easier to show that it is also normal, but anyway, so if that's normal, this is also normal. So this remark helps us to show that this is also normal. Why? Because in fact we have 1 over n x1 plus 1 over n x2 plus 1 over n xn, and if each one is normal, then when we multiply by something they are normal, then we have sum of normal random variables. So normal, normal, and so on. So it is like this one, that is, we are multiplying by some constant. So then we add them, and that is also normal. So let's see what the expected value and variance of this one is. So we need expected value of this. So that is this thing is in fact. Well, let's just write it 1 over sigma as a sigma. We know that expected value commutes with summation, so this will be 1 over n. The 1 over is constant comes out, and it's also sigma can be written out of here. And e of xi is mu, so I have 1 over n times n mu, which is mu. And what is variance of this? And I'm assuming again they are independent. Variance of x bar n. That is e of this thing again. Sorry, that's variance. Variance of this. Let's write it like this: 1 over n x1, 1 over n x2. 1 over n xn, and remember these are independent, so when you multiply by n a constant, they are still independent, and so this variance split, commutes with the addition, but we get 1 over n squared. So we have 1 over n squared variance of x1 plus dot 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 1 over n squared variance of xn. Now each one of them is sigma squared, so I have 1 over n squared sigma squared, or sigma squared over n squared. But, sorry, there's no n here. That's n sigma, right? Times n sigma squared. So I will get sigma squared over n, not n squared. Sigma squared over n. Okay, so the x bar, in fact, you can say that this is like sample mean, right? Sample mean, which I discussed before, that the sample mean is a random variable because each one of them is a random variable, is in fact has normal distribution with this. So let me erase this thing and write it here. The sample mean has this interesting distribution. So sample mean x bar n will be normal with mu. It's interesting that it's mu, but the variance is in fact divided by n. Okay, so that was the sum of normal random variables. When you add them, you will get this. And you will see, I guess there are many problems that has been assigned to you which are related to this. And another thing is that the central limit theorem. That is amazing. So let me erase this and discuss the other one. So the CLT, the premise is this. So we have a sequence of random variables, x1, x2, x3, blah, blah, blah. And they have the same distribution, and let's assume that they are also IID. And remember, the IID was in fact that what we also call sample. So the sample was like, but anyway, this is infinite. So usually sample is finite. But remember that there was some relation between these two notations. So it means that they are independent and they are identically distributed. So you can stop at some n here, okay? And this is like sample now. So we have a sample of size n, and they come from some distribution with some parameter theta. This parameter is like a vector, which means that it can be more than one, which for normal distribution we have two, mu and sigma squared. But it can be one, like for exponential, which is just lambda. Okay, so we really don't know what that distribution is. We don't need that for the CLT. But we need this thing. Remember when we were sampling, we assumed that those agents that are doing the sampling are doing it independent of each other. So they are independent, and since they are sampling from the same, distribution, the same population, so each one has the same distribution, the same as the other one. So let's see what you're talking about. We are, remember if this was in fact, if they were, say, normal, if they were normal, what happened? If that was normal, then the x bar n was normal with mu and sigma squared over n, right? So this is not normal. If normal, this is important. If normal, but they are not normal. So they can be, but not necessarily. So let Zn be that x bar n, subtract mu, and then divide by its variance. Sorry, it's sigma over square root of n. That's its standard deviation. So let's write this down. Then Zn has some distribution. We can relate that to a distribution, but it's like I'm subtracting two fixed numbers. A fixed number and dividing by a fixed number. Then central limit theorem says that this, in fact, this thing, as n goes to infinity, approaches normal 0, 1. Okay? This approaches normal 0, 1. That is amazing. That is, in fact, how does it approach? In fact, it means that that in distribution, it approaches this. So the distribution of this, whatever the Zn is, approaches normal 0, 1. But what does this also mean? It means that if we sample from any distribution, so the interpretation is this. So let's write it as remark. The dist theta does not have to be normal. It has to be normal. Okay? But this doesn't have to be normal. But what happens, even if it's not normal, for large n, Zn is normal. 0, 1, or let's say almost. Right? So that's amazing, which it means that we don't care what the distribution, not we don't care, we don't know what the distribution is. In fact, we are going to study the distribution, but we know there is some distribution. So that's our assumption that this population, whatever we are studying, has some distribution. And that distribution is not known. So we are studying something about that population, for example, the average age, the average something, or the variance of something, blah, blah. And this theorem tells us, okay, we don't care what that is. It's amazing that as we change the number of agents and we set it higher, so if the number of agents that are taking sample gets large enough, then we have, if it is large enough, this, say, this Zn approaches or is almost normal. It's almost normal. So what we can do here, we can say, okay, we really don't care what the distribution is. In fact, we are studying that. So we take some large sample, say, like 10 million. No, 10 million is too much, but I mean, no, maybe not. But anyway, so large sample, and we find, in fact, we will see that then we find that it's say sample mean and the sample variance, and then that Zn, in fact, well, that will be something else. But if we can find the mu and sigma, then we divide it this way, or I mean, we subtract and divide, then this is almost normal. So we will see how this thing is used in statistics, in fact. So this is the CLT, and I'm not sure how much you appreciate this fact that this distribution is really not known and is not normal, not necessarily normal. But the CLT, in fact, gives me normal distribution. Now, sometimes I think one reason that we who do statistics or mathematical statistics or whatever, we really love this normal distribution is because this thing, in fact, mathematically is, I mean, in the limit, mathematically, this gives me normal. So when we find the limit, it's interesting that the limit gives me a normal distribution. If it gave me something else, that would make a big difference, but it mathematically gives me, that limit gives me a normal distribution. Well, as I said, I have given some kind of proof that I guess it's acceptable at this level, that in fact it is the mathematics that gives me this normal distribution as the limit. So so we stick with this, and it is in fact an interesting and important theorem in all mathematics and probability and blah blah blah. Okay, so I guess most of what I wanted is I'm done. So let me stop this and then continue with something else.